The last group of offline RL algorithms that I'm going to discuss today are model-based offline RL methods. So far, all of the offline RL methods we talked about are model-free, but actually model-based methods are a pretty nice fit for offline RL because you can take all of your data, you can train a model on that data as long as you want, get a really good model, and then use that model to obtain a good policy or even just plan with that model directly. So how does model-based RL work? Well, we already know this. We train our model using our data. We would use that model either to get a policy or just to plan directly. And ordinarily, we would then collect more data, right? But if we don't collect more data, then we have a little bit of a problem. It's a similar kind of problem as the one that we had with the Q function. So just like with the Q function, the model essentially is trying to answer what-if questions. What if we were to go back to one of those states in our data set and take different actions? What kind of states would we end up in, and what would happen then? So if you remember back in our discussion of model-based RL, we talked about Dyna-style methods. Dyna-style methods are ones that use the states and actions collected in the real world as starting points for short model-based rollouts. And the first two model-based offline RL methods we'll discuss are basically Dyna-style methods adapted to the offline setting. So what goes wrong in the offline setting when we don't collect any more data? Well, analogously to how for the Q function we could discover these adversarial actions that cause the Q function to erroneously overestimate, for a model-based method, the policy could learn to take actions that trick the model into going into states with very high reward because those states are out of distribution. So we still have the out-of-distribution actions problem, and now we also have an out-of-distribution states problem for the model, because the policy can take some crazy action, fool the model into going into an out-of-distribution state, and from that out-of-distribution state, the model would then go to an even more crazy state. And the policy can learn to exploit this to trick the model into going into states with a high reward, even though that would probably not actually happen in reality. So intuitively, in order to repair this problem, what we need to do is somehow modify these model-based methods so that if the policy starts tricking the model to going into crazy states, it gets some kind of penalty, and the policy is then incentivized to change its behavior to come back to regions that are closer to the data. So first, I'll discuss methods that essentially modify the reward function to impose a little penalty. And the particular method I'll cover is called MOPO, Model-Based Offline Policy Optimization. There's a kind of two methods that are very similar conceptually, MOPO and Moral. I'll talk about the MOPO version, but they're pretty similar, and I would encourage you to actually check out both papers if you're interested in this topic in more detail. They have slightly different analysis and slightly different forms for the penalty. But the basic idea in both cases is to essentially punish the policy for exploiting the model. So the way that we've punished the policy is by actually changing the reward function in some way, or in general changing the model-based MDP. So one way that we can change it is to have the reward function assign a little penalty, which I'm denoting here with the letter U, for going into states where the model might be incorrect. So U is essentially an uncertainty penalty, and all we're going to do is we're going to add this uncertainty penalty and then use any existing model-based RL algorithm. I'll explain the particular choice of uncertainty penalty that we can use in a second, but first I want to describe the intuition behind what this is going to do. So if your policy ends up choosing some action that fools the model into going into a state with a high reward, but that transition is erroneous, then we want the uncertainty penalty to be large in those situations. So the uncertainty penalty basically has to quantify how wrong the model is. If the model goes into an erroneously good-looking state, then the model must have done something wrong, and if we have a good uncertainty penalty, it should be able to catch that. So essentially, the uncertainty penalty is supposed to punish the policy enough that exploiting is not worth it. And that's why we have to choose the multiplier lambda carefully, but if we choose it carefully so that the penalty always costs the policy more than it gains by cheating, then the policy will change its behavior and avoid those crazy out-of-distribution states. Technically, the condition on U that we need to satisfy is that U should be at least as large as the error in the model, measured according to some kind of divergence. Now, this is not an easy quantity to quantify because, in general, you don't actually know how right or wrong your model is. So the way that we would do this in practice is we would use one of those model uncertainty techniques that we discussed in the model-based RL lectures, something like an ensemble. So one common way to do this is to train an ensemble of models and measure the degree of disagreement among the different models in the ensemble as a proxy for this error metric. But in general, getting good error metrics, getting good estimates of U that are actually greater than or equal to the true model error is an open problem. So there isn't a great way to do it that is guaranteed to work every time. But ensemble disagreement is one common choice. Let's talk a little bit about the theory behind this. So let's say that we can find a way to estimate U that does in fact provide an error metric that is always at least as large as the true error in the model. Here's an interesting result that we can show. So there are two assumptions here. The first assumption basically is that our value function is expressive enough that we can represent the value accurately. So if we're using large neural nets, we can more or less assume that this is true. The second assumption is that assumption on U. And this is a very strong assumption. It says that the model error, the true model error, is bounded above by U, meaning that U is at least as large as the true error of the model as measured by some divergence metric like total variation divergence. A to M here is the true return of the policy that was trained under the model represented by M. Epsilon U is the expected value under the model of this error metric of U. So what the above equation is showing is that if we train a policy pi hat using our model, then the true reward of that policy will be at least as large as the best policy we can find minus its expected error. So we can find the best possible policy, but optimized against a different objective, against the reward minus the error. And we can guarantee that our learned policy will be at least as good as that. Another way to interpret this is to introduce this symbol pi delta. And pi delta is the best policy that exists according to the true return, not the model, but according to the true return. So pi delta is the best policy under the true return for which the expected value of the error, the expected value of U, is bounded by delta. So it's basically the best policy that doesn't visit states where the model might be incorrect, where that latter phrase is quantified as the average error of the model is less than or equal to delta. What this equation 12 is saying is that the model that we learn, so the policy that we learn under our model will be at least as good in terms of its true return as the best policy whose average error is bounded by delta minus an error term that depends on delta. So if we choose delta to be very small, then we will actually improve on this. Okay, this might seem a little cryptic, but this theorem has a few interesting implications. One implication is if we substituted in pi beta, the behavior policy, well, we would expect that the error of the model under the states visited by the behavior policy will be very low, close to zero, because those are the states that are actually used to train the model. So if delta for that is very low, it's close to zero, then we would expect that this equation 12 would essentially guarantee that the learned policy is at least as good as the behavior policy, which means that we very likely improve over the behavior policy, or at least we don't do worse. The other thing that this can quantify is the optimality gap. So if we plug in the optimal policy pi star, then the policy that we learn is at least as good as pi star minus a penalty for how wrong the model is on the states that pi star visits. So if the model is very accurate for the states and actions visited by the optimal policy, then this would guarantee that we will recover something close to the optimal policy. So these are interesting results to show that essentially these results tell us that this method will improve over the behavior policy and it can get something close to the optimal policy if your model is accurate for the states and actions visited by the optimal policy. Now, whether the model is accurate in that case or not really depends on the data that you have. This is a little bit of analysis, and hopefully that kind of gives you a taste for the types of results that in general we can try to show for offline RL methods. There's a kind of a more evolved version of this idea where we can actually apply a CQL-like principle to model-based offline RL. And that's a newer algorithm called combo. So the basic idea behind combo is just like CQL minimizes Q values of policy actions, we can minimize Q values of model state action tuples. So here's our dyna picture again, and we're going to have a loss function for our critic that looks very similar to the CQL loss from before, where we're minimizing Bellman error, but now we're going to be using data from the model to do this, so it's a dyna style method. We're going to be maximizing the Q values in the data set, and then we'll be pushing down on state and action Q values from the model. So we're trying to make Q values under the model be worse and Q values under the data set be better. And the intuition here is if the model produces something that looks clearly different from real data, it's very easy for the Q function to make that look bad. But if the model produces very realistic states and actions, the ones that are indistinguishable from the ones in the data, then these two terms should really balance out. So it's a somewhat GAN-like idea in a sense. And this is nice because we're not actually changing the reward function, we're just imposing this additional regularizer on the Q function that says, Q function, try to make the model-based states and actions look worse. And if you can't make them look worse than the data, that means that they're indistinguishable from the data, which means that the model is actually being correct. The model is not producing states and actions that look unrealistic. And this actually ends up working a little bit better than Mopo and Morel. Now, both of the algorithms I described so far are dyna-style algorithms. We can actually do offline RL in a non-dyna style way. We can do offline RL where we actually don't learn a policy at all and we just try to plan under the model, but we still need some mechanism to compensate for out-of-distribution actions. So there are a few ways to do it. One recent paper that I want to tell you about is something called the trajectory transformer. So the basic idea here is that we would train a joint state action model. So we're not just going to train a model that predicts future states, conditional current states and actions. We'll train a model over entire trajectories. So this model will provide us with probabilities of state action sequences by just doing density estimation on the trajectories in the data set. And I'm going to use a subscript beta to denote that this distribution, of course, depends on the behavior policy. And intuitively, what we're going to do with this distribution is we're going to optimize for a plan, for a sequence of actions that has high probability under this distribution, which means that we will avoid actions that are very unlikely in the data, which will avoid out-of-distribution actions. And then the other thing we can do is, once we're doing offline model-based RL, we can use a very big and expressive model, such as a transformer. That design decision is largely orthogonal to the first point, so you could do the number one with any model class. But if you're doing offline RL, it's actually very convenient to use a very large, very expressive model class, because you don't have to do active data collection, you don't have to update your model between trials, which means that it's okay for the model to be really big and computationally expensive. So you want basically the most powerful density estimation model you can get your hands on. And these days, if you want a really powerful sequence density estimation model, a transformer is a good choice. Although the same thing could be done with other kinds of density estimators. So I have a reference at the bottom here to a paper that actually describes this, an approach of this sort. And the model that's used there actually is a transformer model. And in order to model multimodal distributions, it actually discretizes the entire trajectory. Now, you can't discretize the trajectory as a whole because there will be exponentially many discrete states. So instead, the discretization is done per dimension of every state in action. So it's not a sequence model over time steps. It's actually a sequence model over dimensions of states and actions. So transformers and other sequence models operate at the level of tokens. So the first token is the first dimension of the state at the first time step. And based on that token, the model predicts the second dimension of the state at the first time step. Then it predicts the third dimension, the fourth, and so on, until you get to the last dimension of the state at the first time step. And from that, it predicts the first dimension of the action at the first time step, Based on that, it predicts the second dimension, and so on and so on and so on, until we get to the last dimension of the first action, and then you predict the first dimension of the state at the second time step, and so on until you get to the very end of the trajectory, until you get to the last dimension of the last action. Now, I drew this model here as an autoregressive sequence model, which you could do with something like an LSTM, but you can also do this with a transformer. You need a causal mask for the transformer, so this would be something that we would do in something like a GPT-style model. If you're not too familiar with transformers, don't worry about this too much. This is basically the main idea is that any kind of sequence model could be used. Now, one nice thing about this is because you're modeling state and action probabilities, you can make very accurate predictions out to much, much longer horizons. So this problem of accumulating errors is a big problem if you're selecting new actions, different from those seen in the data set. But if you're restricting yourself to actions similar to those seen in the data set, then you can make very accurate predictions very far into the future. So this animation is actually showing the trajectory transformer making predictions for the humanoid hundreds of steps into the future. So this is not a simulation, this is actually just a prediction from the model. And then you can use this model to do planning. Now, you can use many of the same techniques for planning as what we discussed in the model-based control lecture a few weeks ago, but it's important to take the action probabilities into account because you don't want the plan to produce actions that have a low probability under the data. One approach to this would be to use beam search, which already works quite well with these sequence models, but instead of using beam search to maximize probability, use beam search to maximize the reward. So, given the current subsequence, so let's say you've decoded up to time step 3, select the next token from the model by just sampling it from the probability distribution. Sample many tokens, let's say you sample k tokens, and then you store the top k with the highest cumulative reward. So that's basically beam search. So you have k prefixes for each one you sample k tokens, sort them, and take the top k. And top here means top in terms of total reward. And you do this one time step at a time. That's the basic high-level idea. There are some details to get this to actually work, but that's the principle. Now, of course, you could use any other planning method. You could use MCTS with this. You could use even differentiable things, although you would have to be careful to turn those discretizations into continuous values. The important thing is that you need to make sure that you're maximizing reward and also taking the probabilities into account. So the beam search approach takes probabilities into account because when it samples those k tokens, they're sampled from p beta. So they're sampled from a distribution of tokens that have a high probability under the data set, and then you select the best one among those. And that's okay. So why does this work? Well, generating high probability trajectories avoids out of distribution states and actions because you're actually using p beta, both to select the states and the actions. And using really big models works well for offline RL because you can use lots of compute and capture complex behavior policies. So you can capture complex dynamics, you can also capture complex behavior policies.